All right, so far we've developed the weak form, determined an approximate solution, and developed the finite element model for an element. This element had been isolated from the mesh, and now what we have to do is put everything back together because we currently have n equations and 2n unknowns. So in order to get the finite element equations for the total problem, we have to put the elements back in their original position. In doing this, we have to make sure that we have our solution is continuous and that the source terms are balanced. So we want our continuity of our primary variable and a balance of our secondary variables. So we're going to impose two boundary conditions. So if I have node I of element E connected to node J of element F connected to node K of element G, then I'm going to require that UI is equal to UJ is equal to UK of element G. When we connect our elements in series, this requires that pretty much what I'm saying is here's one element. Here's element omega. I have some function. I have U1 on this side, and I have UN on this side. And then I have another element. This is element E plus 1. And I have some more function. I have the value UE plus 1, 1. I have our value UE plus 1, M. For continuity purposes, I need UN of E equal to U1 of E plus 1. These 2 points have to be the same. Makes sense because they're at the same point if they connect. I also have a Q1 on this side, a Qn on this side. I have a Q1 of E plus 1 on this side, and I have a Qm on this side. So the second condition that we're going to look at is for the same three elements that I said previously, we need a balance of secondary variables. So Qi of element E plus Qj of element F plus Qk of element G is going to be equal to Q big I, where I is my global node number that I'm at. Essentially, up here, I need Qn of E plus Q1 of E plus 1 to be equal to Qi. So in our figure above, we have Qn of E plus Q1 of E plus 1 is equal to 0 for Qi, and 0 for no external point source. And it's I if there's an external point source. So in order to force the above balanced secondary variables, we need an expression in this form in our finite element equations. What we're doing is we're adding the ith equation of element E to the jth equation of element F and the kth equation of element G. For the case that I have drawn, the nth element of element E has to be added to the first element of the first equation of element E plus 1. So for element E, we're going to take the nth equation, which is the sum j equals 1 to n knj uj equals fn plus qn. And then for element e plus 1. This is sum from j equals 1 to n, k1j, uj, plus 1, plus 1, equals f1, e plus 1. So I want to add them. So what I'm going to get, I'm going to get the sum from j equals 1 to n of knje uje plus k1j e plus 1 ue plus 1j equals fn plus f1 plus qn plus q1. And this is just qi. So this reduces the number of unknowns from 2n to n plus 1 in a mesh of linear elements. We're going to also note that the first equation for the first element and the last equation of the last element remain unchanged, except for renaming of our variables. We can rewrite the left-hand side in terms of our global nodal values as kn1, u1, kn u1 plus kn2 u2 knn un plus k11 u1 plus k1n un this is the same as saying kn1 un plus kn2 un plus 1 plus knn un plus n minus 1 So what does this big, long, nasty equation get me to? Because there's also a kn1. If I was to group some like terms together, I would have kn1 un plus kn2 un, so on. I would have a big, long equation. So what's this going to get me to? So for a linear mesh, n is equal to 2, and we're going to get k11 u1 plus k12 u2 is equal to f1 plus q1. This is our unchanged first equation. Then I want to get k21 u1 plus k122 plus k11 u2 plus k12 u3 f11 plus f21 plus q12 plus q21. Keep going until I got down to the end. I have k21n un plus kn22 un plus 1, so it's fn, which is our other unchanged equation. So this is our assembled equation is assembling very similar to how our discrete system's assembled. They contain the sum, the coefficients, and the source terms at the common nodes, which if we were to write this in matrix form, we would get K111, K112, K121, K122, plus K111, K112, so K2, K221, K222, plus K311, big old 0 over here, big old 0 over here, Kn minus 122, plus Kn11, Kn12, Kn21, Kn22, times U1, U2, U3, Un minus Un plus 1 is equal to F11, F12 plus F21, F22 plus F31. And this is how any system of linear equations is going to assemble. So you don't have to do all that wacky algebra again. If you are using linear elements, this is what you're going to get. This is really only true if elements are connected in series. We are only going to assume elements are connected in series in this course. So this is what we're going to get for linear elements. So at this point, all we need to do in order to solve is apply our boundary conditions. Once we apply our boundary conditions, we can come up with our solution equations. Again, it's standard practice to solve the condensed equations for the unknown primary variables first, and then go back and calculate your secondary variables. The last thing that computer software does is called post-processing of the solution, where we now know the value at distinct points. We have to go back and use our interpolation functions to interpolate before these between these points. So we would have u of x is equal to u1h, u2h, unh, which is our sum from j equals 1 to n, uj1, psi 1, and so on. So we can also find derivatives. The derivatives can be found by differentiating our equation. So du dx would be duh1, which is the sum from j equals 1 to n of uj1 d psi j1 dx to dun dx of j equals 1 to n of unj. So this is actually what SolidWorks and everything does for you. So we're actually going to work through an example. We wish to use the finite element method to solve the following boundary value, to solve the following differential equation with given boundary conditions. we want to solve the equation minus d squared u dx squared minus u plus x squared is equal to 0, where u of 0 is equal to 0 and u of 1 is equal to 0. So the first thing we're going to do is compare our given ODE to the ODE that we did all of this math for, so we don't have to redo everything that we just derived. So by comparing these two equations, you get that A is equal to 1, C is equal to minus 1, and F is equal to minus x squared. All right, so now that we know A, C, and F, we can go through and calculate our stiffness matrices. We can use our previously derived weak form and our previously determined coefficients matrix, which, as we remember, Kij was the integral of d psi I dx dj dx minus d psi I d psi j, and F would be xa to xb of minus x squared psi I dx. For 4 linear elements, our above equations become, so let's do our stiffness one first. It's A over H, 1 minus 1, 1, plus CH over 6, 2, 1, 1, 2. So H is equal to 1/4 because our domain goes from 0 to 1 and we have 4 elements. So it's 1 divided by 1/4 times 1 minus 1 minus 1, 1 plus minus 1 times 1/4 divided by 6 times 2, 1, 1, 2, which is equal to 4 minus 4 minus 4, 4. Minus 1/24, 2, 1, 1, 2, which is equal to 3.9167 minus 4.0417, 417. And this is valid for every single one of our 4 elements. So now we have to go back and calculate F. So Fi is equal to the integral from xa to xb of f psi I of x dx, which in our case is the integral from xa to xb minus x squared psi I of x dx, which is equal to minus the integral from 0 to h of x bar plus xa squared psi I of x dx bar. So FE1 is going to be minus the integral from 0 to h of x bar plus xa times 1 minus x bar over h dx bar, which is equal to minus h times xa squared over 2 plus xah over 3 plus h squared over 12. If h is equal to 1/4, we get minus xa squared over 8 minus xa over 48 minus 1 over 768. So now we need FE2, which is equal to the integral from 0 to h of minus x bar plus xa times x bar over h which is equal to minus xa squared over 8 minus xa over 24 minus 102 over 56. So now that we know what FE1 and FE2 are, we're going to evaluate for each element. So for element 1, xa is equal to 0. So I'm going to draw my domain that goes from 0 to 1, and I wanted 4 elements. So I have element 1, 2, 3, 4, and I have increments of 1/4, 1/2, 3/4, and 1. xa is always the beginning, so for element 1, xa is 0, so you're going to get f11 is equal to 0 minus 0 minus 1 over 768, which is minus 0.001302. You're going to get f12, which is 0 minus 0 minus 1 over 256, which equals minus 0.003906. So for element 2, xa is now equal to 1/4. So you get f11, you get f21 is equal minus 0.014323, and f22 is minus 0.022135. You can do it for element 3. xa is now equal to 1/2, so you get f31 is equal to minus 0.042969. f32 is equal to minus 0.05599. And then we have element 4. xa is now equal to 3/4. Get f41 is equal to minus 0.08724. And f42 is equal to minus 0.10547. So now we're going to assemble everything together. It's going to assemble in series, so along the diagonal, we're going to sum our elements together. Oops. So this is our assembled stiffness matrix. Which is equal to 3.9167 Now we're going to assemble F. So it's going to be F11, F12 plus F21, F22 plus F31, F31 plus F32 plus F41 and F42, which is equal to minus 0.00130, 0.823, 0.06510, 0.14323, 0.10547. And Q would equal Q11, Q12 plus Q21, Q22 plus Q31, Q32 plus Q41, and Q42. So we would apply our the last thing we would do was apply our boundary conditions. Our boundary conditions as stated are U1 is equal to 0 and U5 are equal to 0. So we're going to eliminate the first and fifth rows and columns to get our condensed system, which is 7.8333 minus 4.0717 minus 4.0417, 7.8333, times U2, U3, and U4 is equal to minus 0.01823, 0.06510, 0.14323. Our solution becomes U1 equals 0, U2 equals minus 0.02323, U3 is equal to minus 0.04052, and U4 would equal minus 0.03919, and U5 is equal to 0. The secondary variables can be obtained from the element equations or from the derivatives. Q11 is minus A duh dx at x equals 0, which is U1 minus U2 over H, 0.09293. Q42 is A du dx at x equals 1, which is U5 minus U4, which is 0.15676. If you were to use the element equations, you would get slightly different answers. Those are more accurate if you have a point source function f. Now, what if we were to solve the same problem assuming two quadratic elements? How would that look? We still know A and C. For two quadratic elements, I have 0, a half, 1. So H is equal to 1/2 now. So I want to go look up my equations. I want to say that KE is equal to A over 3H, 7 minus 8, 1, minus 8, 16 minus 8, 1 minus 8, 7, plus CH over 30, times 4, 2, minus 1, 2, 16, 2, minus 1, 2, 4. Which if I plug in my numbers, gives me 4.6000 minus 5.3667 2.6833 minus 5.3667, 10.400 minus 5.3667, 0.6833 minus 5.63367, 4.6000. Now, we do have to recalculate f. So FE1 is equal to the integral from 0 to h. Please, if you are working in quadratic, always convert from 0 to h and from xa to xb. It's going to be FE psi 1 dx bar, which is minus 0 to h x bar plus xa squared, 1 minus 3 x bar over h plus 2 x bar squared over h squared dx bar, which equals minus h over 60. I'm just going to plug everything in, which equals minus 1 over 480 times 40 xa squared minus 1. FE2 is minus 1 over 120 times 3 plus 20 xa plus 40 xa squared. And F3 is equal to minus 480 times 9 plus 10 xa plus 10 xa squared. So for element 1, xa equals 0, so F11 0.00208, F12 equals minus 0.02500, F13 equals minus 0.01875. So for element 2, we have F21 is equal to minus 0.02500. Nope. It's minus 0.01875. F22 is minus 0.19167. And F23 equals minus 0.08125. So now we need to assemble things. I want to redraw my picture here. So I have my two elements. I have my element 1 and my element 2. And element 1 has nodes 1, 2, and 3. And element 2 has nodes 1, 2, and 3. So we have element 1, node 3 connects to element 2, node 1. And that's how we're going to assemble our matrix. So it's K111, K112, K113, K121, K122, K123, K131, K132, K133 plus K211, K212, K213, K221, K222, K223, K231, K232, K3, K233. So that is our assembled stiffness matrix. And our source vector would be F111, F12, F13 plus F21, F22, F23, so our condensed system of equations after applying our boundary conditions become 10.4 minus 5.3667, 0, minus 5.3667, 9.2, minus 5.3667, 0, minus 5.3667, 10.4, times U2, U3, U4, minus 0.025, minus 0.03750, minus 0.19167. And in this case, our solution is U1 equals 0, U2 equals minus 0.02345, U3 equals minus 0.04078, U4 is minus 0.03947, U5 is equal to 0, Q11 is equal to K11 U1 plus K12 U2 plus K13 U3 minus F11, which is 0.1006, and Q42 equal to 0.26521, which is very similar to what we got for our linear approximations. So those are the steps in solving any problem that you're going to have for homework. This is also the end of all of the theory. So next we're going to start working on how to use SOLIDWORKS.